Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 7 on Introduction to Exponential Functions. So here we go. This is what this entire unit has really been driving towards, introducing you to a new type of function, right? Primarily what we've had so far are linear functions and then kind of offshoots of linear functions like piecewise linear or step functions or absolute value functions. Ultimately, every part of those functions still sort of lied along a straight line. But exponential functions are the first ones that we're going to look at whose graphs actually lie along a curved line as opposed to a straight line. So let's get right into it. All right, very, very important. Exponential functions. We've mainly worked with linear functions, which are characterized by having constant rates of change, right? Constant slopes. We now introduce another important type of function known as an exponential function. One could even argue exponential functions are the second most important type of functions, the most important type being linear. So let's take a look at an exponential function. Consider the exponential function f of x equals 8 times 2 raised to the x. Answer the following. Evaluate each of the following and indicate what point must lie on the graph of f of x based on each. All right, well, we have done a ton of work with both function notation and evaluating exponential expressions. So I'd like you to pause the video right now and try to evaluate each one of these function notation problems, and don't forget to tell me what point must lie on the graph of f of x based on your calculation. Go ahead and do that. All right, let's do it. So first things first, we've got f of 2. All right, f of 2 is going to be 8 times 2 to the second, right? That's going to be 8 times 4, and that's 32. So that means that the point 2, 32, look at how big that's gotten, 2, 32 must lie on the graph. Let's take a look at f of 0. That's 8 times 2 raised to the 0. Remember, anything raised to the 0 power is equal to 1. So that's just 8 times 1, which is 8. That tells me the point 0, 8 lies on the graph. I'd also like to put a little star here. That's the y-intercept of the graph, right? Any output where the input is 0 is the y-intercept. And finally, f of -1 is going to be 8 times 2 to the minus 1. Remember, that's going to be 8 times 1 over 2 to the first, and that's equal to 4. So that means the point -1, 4 lies on the graph. Let me just circle all these things. Given that each one of them is part of the answer to the problem, there we have it, right? Now again, these last two, f of 0 and f of -1, rely on the fact that you feel comfortable now with 0 exponents and negative exponents. I certainly hope after all of the lessons that we've done in this unit so far, especially the last one where we did a ton of work with negative exponents, you feel comfortable with that. Now, let's do a couple average rate of change problems. It's been a little bit since we've done that, and I kind of want to keep these points sitting up there because they are points on the function. Let's take a look at letter B. Calculate the average rate of change of f of x over the interval -1 is less than or equal to x, which is less than or equal to 0. Fantastic. Let's do this one together and remind you what's going on, right? Now, -1 to 0 in terms of x means that we're really going from the point -1, 4, I'm just taking this from the last problem, to the point 0, 8. And what I'm really doing whenever I do an average rate of change is I'm doing the change in the function value divided by the change in the x value. That means I'm going to take this y value and I'm going to subtract this y value, and I'm going to divide by this x value minus this x value. Be careful there. That's going to be 4 divided by 1, and that gives me an average rate of change of 4 units. Now, never forget what that really means. That means that as x increases by 1 unit here, y has increased by 4 units. That's all it's saying. Now, part C, calculate the average rate of change over the interval 0 to 2. All right, well, let's start the problem together and then have you finish it. Again, we know that at x equals 0, the point is 0, 8, and we know at 2, x equals 2, the point is 2, 32. Why don't you go ahead and take those 2 points, again, we got those simply from the last problem, and calculate again the change in the function's value, the change in the output, divided by the change in the input. Pause the video now and go ahead and do that. All right, let's do it. So here we go, right? The change in the function over the change in the x is going to be 32 minus 8 divided by 2 minus 0. 32 minus 8 is going to be 24 divided by 2, and that's equal to 12. Average rate of change is equal to 12. All right. So over the interval -1 to 0, this function is changing at a rate of 4 units of increase in y per 1 unit of increase in x. Over the interval 0 to 2, on the other hand, it's changing at 12 units of y per 1 unit of x. Never forget what the average rate of change is telling you. How much does y change per 1 unit of change in x? Now, letter D is actually very important. Let's take a look. What does comparing the answers from B and C tell you about this function explain? All right, so I want to go back to this. Right? I want to look at those two. Now, there's one thing immediately that it should tell us, and that's what I'm really hoping you get out of this. Pause the video now, and what does it immediately tell you that this value is 4 and this value is 12? Well, look, you could tell me a lot of different things. You could tell me, well, the rate of change here is 3 times the rate of change here, and that would be correct. You could say that the rate of change is getting faster as x gets larger, or the rate of change is getting larger as x gets larger. That would also be true. But at the essence, what I really want you to understand is that because these two numbers are different, this function can't be linear. All right, I'm going to say that again. Because this average rate of change and that average rate of change are not the same, this function can't be linear, right? Linear functions always have the same average rate of change no matter what 2 points you pick to calculate it. So at the end of the day, the one thing I really want you to get, first and foremost, is this is not a linear function. Because the average rate of change is not constant. Or because the average rate of change changes. Okay, that's not funny to anyone but me. All right, anyway, so now what we want to do, I think, is we want to get a picture of what this thing looks like. So let's take a look at letter E. Using your calculator, draw a sketch of this function on the axes below using the window indicated. All right, so look, I'm choosing the window because I've had a little bit of experience here. So we're going to bring out our TI Inspire right now, and we're going to take a look at entering this function, 8 times 2 to the x. Let's bring it out, all right. I'm going to add a graph. Okay, I've got my f1 of x right away. So that's 8 times 2 raised to the x. Love to get that thing out of there. No, it's not going to go away, is it? There we go, maybe. Anyway, whatever, enter. Okay, well, that doesn't do too much for me yet because I haven't set my window to be the same as this window. So let's go in and do that now. I'm going to hit my menu button, go down to option 4 for window, and then I'm going to go into window settings. Looks like they're telling me that I should go from -4 to 4 along the x-axis. I'm not going to worry about the scale. And I'm going to go from -10 up to 150 on the y-axis. And let's take a look. Look at that graph, right? Definitely not linear, right? There is no way you can tell me this falls in a straight line. I mean, I don't even need a ruler to tell it. That is not a straight line, right? Not only that, but at the beginning it's quite flat and then it gets steeper and steeper and steeper. Sometimes you'll hear people talk about things having exponential growth. Oh my goodness, that's growing exponentially, right? And this is what they mean by it. At first it's growing very slowly, and then it starts to ramp up higher and higher and higher, right? And we could see this, regardless. By the way, remember how we pointed out in part A that 8 was the y-intercept. It's a little bit hard to tell that, even if I make this thing huge, but you can kind of see that the y-intercept is just a little bit below 10 there. Now, I want to sketch this thing out. I don't need to make it perfect, don't get me wrong. I think I'm going to make this go on my handheld only so I can keep it right in my front. all I really want to do is get this general shape. Some people will describe this almost with the term a hockey stick-like graph, all right? If you've ever seen people play hockey, right, their sticks kind of come down and then they flatten out. And that's sort of what we got going on here. It's very, very flat, and then it curves up and becomes very steep, all right? And we saw that, right? Immediately, by the time we hit x equals 2, our output was already at 32, right? At x equals 1, it would be only 8. At x equals 0, it would, at 1, it would be 16. At 0, it would be only 8. But at 2, we're already at 32. And that's because, right, if you think about this, let me move this out of the way for a second. The base of this function is 2. Every time x increases by 1, we get to multiply by 2 again. And by 2, and by 2, and by 2. And if you think about our geometric sequences that we looked at earlier in this unit, it makes a lot of sense why this thing would be growing so quickly. All right, we're going to bring this thing back out eventually. I'm going to go back to my side screen, put my calculator away, go back into my full view, and let's keep going. So the basic equation of an exponential function. Exponential functions are all about multiplying an original quantity, a number, by a constant, another number, to a certain exponent. So let's take a look at that sort of general form of an exponential function. Y equals a times b to the x. We're taking some number. In the last problem, that number was 8. We were multiplying it by a base. In the last problem, that number was 2, raised to a power. Now remember that 8 was our y-intercept, right? This number a is the y-intercept, and it's the y-intercept because if I put 0 in here for x, b raised to the 0 will be 1, 1 times a will just be a. So a is the y-intercept of the graph and b is the base. Sometimes b is given special names depending on the context of the problem. Sometimes it's called the growth factor if the exponential function is increasing, like what we just saw. Sometimes it's called the decay factor if the exponential function is decreasing. We'll see one of those in just a moment, okay? But, right, a constant times another number raised to a power. Let's work with exponential functions. Now, the behavior of an exponential function will directly relate to the values of a and b. It's all about a and b, okay? Just like, right, when you've got like y equals mx plus b, right, the equation of a line, that was all about the slope, m, and the y-intercept, b. Unfortunately, they both use the letter b in their general form. Those b's are definitely different from each other. So let's take a look at exercise number 2. Consider the function g of x equals 54 times 1/3 to the x. Evaluate g of 0. What point does this indicate on the graph of g? All right, go ahead and do it, right? You know how to do function notation and you know how to work with exponents. Go ahead and figure out g of 0. All right, let's do it. So, g of 0 is 54 times 1/3 to the 0, but any number raised to the 0 power except for 0 is equal to 1. And therefore, g of 0 is equal to 54, which is the y-intercept, right? So really, this is just what I was talking about, and I hope you can now understand why, right? Whenever you have a function that has this kind of look to it, a times b to the x, right? When I put x equals 0 in and I get b to the 0, which is equal to 1, I'm always going to get y equals a times 1, or just a, as the output. It's cool. You want to understand, you want to definitely know that this number here is the y-intercept, okay? But you want to know why it's the y-intercept, not just memorize, oh yeah, that number, that's the y-intercept. All right, let's take a look at letter B. Without the use of your calculator, determine the values of g of 1 and g of 2. All right, go ahead and do that. See what g1 is and g of 2. All right, let's do it. So, simple enough. G of 1 is going to be 54 times 1/3 to the first, so that's just 54 times 1/3, or better yet, it's 54 divided by 3, which is going to be, let's see, for some reason my head doesn't want to do this right now. Oh yeah, okay, it's 18. It's 18. G of 2 is going to be 54 times 1/3 squared, and that's going to be 54 times 1/9, and that's equal to 6. By the way, notice, right, G1 is 1/3 of 54, which is 18. G2 is 1/9 of 54, which is 6th. But it's also 1/3 of 18, right? So I went from 54 divided by 3 down to 18 divided by 3 down to 6. The next time I divided by 3, I'd be down to 2, etc. All right. Now, just like before, I'd like to get a sketch of this thing. All right, I want to see what this exponential function looks like. So let me bring out the calculator again. We'll move it over here. I'm going to go into Menu, Graph Entry Edit, Function. All right, I'm going to go back up to F1 and just, what? No, just no. Just no. Let's just open up a new document. I don't know what it's doing there, but we're not playing that game. All right, so it's 54 times 1 divided by 3 raised to the x. All right, enter. Excellent, excellent. Now we need to have the same window. All right, I wish I could make this a bit smaller, but I can't. So I'm going to go into Menu, Window, Window Box. I need -2. My biggest x here is going to be 4. My smallest y is -10 again. My largest y is 100. Ah, there we go. Okay. Still not great. Actually, I think now I'll make this handheld only so that you can see it a little bit better. Okay, take a look at that, right? Very similar graph to before, right? Very similar. All right, one of the big differences, though, is that this function decreases as we move from left to right. And we'll talk about that in a little bit, but this one decreases. It's very hard to tell, but its y-intercept is up here at 54. And again, when I sketch this out on the graph, all I really want is something that kind of looks like this. All right, I don't need to have it perfect. Not that. I'm looking for that hockey stick-like graph. Starts up here, decreases and flattens out as it goes to the right. Before it was flattening out as it went to the left. But there you go, right? Again, certainly not a straight line, certainly not linear. Now, for probably the most important part of this problem, though, let's talk about letter D. Let me get this down a little bit further. Letter D. Why is this exponential function always decreasing while the one from exercise number 1 is always increasing? Fill in the box below. All right, so like before we fill in the box, let me just recall. In the first problem, we had f of x equals 8 times 2 to the x, and this was a function that was increasing. All right, in this particular problem, I probably used f of x again. No, I used g of x. Fantastic. In this problem, I had g of x equals 54 times 1/3 to the x, and that was decreasing. So why? Why was this an increasing exponential function and this was a decreasing exponential function? And I would hope that you can think back to the first 2 lessons from this unit. The first lesson that we did in this unit, we looked at exponential growth and decay, and the second lesson we looked at geometric sequences, both of which are directly related to what we're talking about right now. So what will make the function increase, the exponential function increase? What will make the exponential function decrease? Pause the video now and see if you can write something down. All right, well, the plain fact is it's all about whether or not the number that we're multiplying by is greater than 1 or less than 1. Right? And that was exactly what we had in the first 2 units, or sorry, the first 2 lessons of this unit, right? Whenever our common ratio or our multiplying factor was greater than 1, our geometric sequence increased. And whenever our multiplying factor was less than 1, our geometric series or sequence, decreased. So that's it, right? y equals a times b to the x will increase or grow if the base is greater than 1, and it will decrease if the base is less than 1. Now, I'd get yelled at by a bunch of mathematicians if I didn't throw that in. We will always have the base be positive, okay? In exponential functions, the base is always going to be positive. So I'm often going to say when the base is greater than 1, it increases, and when the base is less than 1, it decreases. A lot of math teachers would want me to say, look, the base is between 0 and 1, and it will be. Okay, so when it's decreasing, we're going to have a number between 0 and 1 because we're not going to have a negative base. All right, but I really want you to think about it as, hey, if I multiply by a number greater than 1, I'm getting bigger. And if I multiply by a number less than 1, I'm getting smaller. That's why here, when I kept multiplying by 2, my result kept getting bigger, it kept doubling. And here, when I multiplied by 1/3, it kept getting smaller. All right. Now that's easy enough, right? And it's actually pretty similar to linear functions, right? With linear functions increased when the slope was positive and they decreased when the slope was negative. Here it's not about positive and negative, it's about whether or not b is greater than 1 or less than 1, right? When we have the increasing case, right, b is greater than 1, we're going to always see a graph that kind of looks like this. The y-intercept again is always that a value. In the decreasing case, where b is less than 1, we're always going to get a graph that somewhat looks like that, again, where a is your y-intercept. That doesn't change at all. A is always your y-intercept. So let's do it. Exercise number 3. For each of the following exponential functions, give its y-intercept and tell whether it's increasing or decreasing. All right, this is so simple, right? I look at this, y equals 8 times 2/3 to the x. Immediately I can say, well, I know this number is my y-intercept. It's equal to 8. Then I look at this number and I say, well, b is equal to 2/3, which is less than 1, and therefore this is a decreasing exponential function. And that's it, right? So in other words, I start at 8 on the y-axis and it decreases. What I'd like you to do is take a look at the next two and tell me what their y-intercept is and whether they're increasing or decreasing. All right, well, for this particular one, right, here's our y-intercept. So our y-intercept is equal to 125. On the other hand, our base is equal to 1.5, which is greater than 1, and therefore this is increasing. All right. In our last problem, I didn't get very original here now that I look at it. Our y-intercept is equal to 56. Our base is again equal to 1.5 because 3/2 and 1.5 are the same number. Sorry about that. But that's greater than 1, and therefore it's increasing. Now, be careful. The reason that I tossed C in there was not to be redundant with B, but it was because a lot of students start to adopt a mentality where if the base is a whole number, it's increasing, and if the base is a fraction, it's decreasing. Don't go there, right? Because you've got some fractions that are greater than 1, and you've got some fractions which are less than 1, and a fraction that's greater than 1 will still indicate an increasing exponential function. So don't get into the habit of thinking, well, if it's a whole number, it's increasing, and if it's a fraction, it's decreasing. That's not the way you want to look at it. The question is, are you multiplying by a number greater than 1, or are you multiplying by a number less than 1? Pretty much that easy. All right, let's take a look at one last problem. Now, to form an equation of an exponential function, right, you need to figure out those two numbers, your a and your b, right? Your a is the starting value at x equals 0, and of course your b is what you're multiplying by every time x increases by 1. And that's really key, right? Every time x increases by 1, what are you multiplying by? So let's try a very, very simple problem along that lines right now. We're going to work a lot more in this unit with creating exponential function equations. So this is just our first attempt. Let's take a look. Find the equation of the exponential function in the y equals a times b to the x form for the function given in the table below. Show or explain your thinking. All right, cool. So what I'd like you to do is pause the video now and see if you can figure it out. And again, it's all about just seeing if you can figure out what the value of a is and what the value of b is. Pause the video now and see what you can do. All right, well, one of the values here should have been relatively easy, which is the a value, right? The a is our y-intercept, right? A is the y-intercept, which must be equal to 10, because that's the output when the input is 0. Now, on the other hand, the b is how much we multiply by each time x increases by 1. Now, we're fortunate in this table that, in fact, x is increasing by 1. And so we can literally just look at this table and say, well, what did I multiply by each time? And I kept this one easy, right? It should be obvious that each time we multiply by 3 to get from one y value to the next y value, so the base must be 3, which means the equation of my exponential function is 10 times 3 raised to the x. And that's it. And we could test it. We could, take one of these other values of x, plug it into this function, and see if it gave us those y values. For now, though, we're going to move on, right? Let's summarize a bit. Today, we saw a very important function for the first time. In theory, you haven't seen exponential functions in any other course besides this one, right? These are important functions because they model situations where instead of adding the same amount each time, you multiply by the same amount each time. They come up all the time in the real world in terms of things that spread exponentially like rumors, right, to things that decrease exponentially like radioactive decay, which I'm sure as a freshman you're very concerned about, radioactive decay. Anyway, there's lots of situations in math, physics, science, chemistry, economics, and all over the place that are modeled with exponential functions, and we'll see much of that as we move through this unit. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.